Hello guys, welcome back to our presentation. Thanks for joining us right after the lunch break. I'm Chiachih Wu from Ember Group. Today in our presentation, we're going to show you our recent research about how we fuzz the NTFS implementation in the Linux kernel. So, and here's my agenda today. We'll start from a brief introduction about who we are, and then the motivation of doing this research, and also some basic idea about file system, Linux file system, NTFS, and all the challenges of fuzzing a new file system, especially in Linux kernel, and how we deal with those challenges with our Paragon fuzzer, and we'll wrap up the presentation with a evaluation and takeaways. But actually, before we introduce ourselves, I'll do something interesting. I'll start from a live fuzzing demo. So let me switch to my terminal. Sorry, I need to. My mouse is not working. Oh, right here. Oh, okay. Okay. So right here, you can see the Paragon fuzzer, and you can check. We already open source it, so you can go to our GitHub repo to reproduce what happens here at home. So yeah, we have a script to run the fuzzer, so you will start fuzzing. And this fuzzer is set up with Linux 6.0, which has the Linux 6.0 in the so-called Linux kernel library inside. So you see the AFL fuzzer screen right here is actually generate file system image and all the system codes about file operations and try to get the kernel crash. And you will see some numbers on your right-hand side, the top corner. And yeah, that's how we evaluate if it works. So we hope by the end of this talk, we can find something interesting. So let's switch back to the presentation slides really quick. So after the agenda, let me briefly introduce ourselves. I'm Chiachih Wu, and the gentleman sitting there is Edward Low. We both work for Ember Group and doing security research here. But actually, Ember Group is a crypto company, so it's kind of weird why we're doing research about it in this kernel, right? Because maybe you know that the blockchain has the blockchain client P2P network, and actually over 90% of blockchain clients running over Linux. So we try to secure the whole software stack of blockchain infrastructure. That's might be the reason. And also, I lead the Web3 security team at Ember, and the Web3 world is actually moving really fast. So you won't be surprised that we have like millions of dollars being hacked every week. So it happens in the Web3 world. So we also work with universities or consulting firms to conduct security research on the cutting edge technology like this one to try to move faster than the bad actors. So that's what we do at Ember Group. So about the motivation, actually this slide reminds me that in my previous 1 decade security research career, I was lucky to dive into Android in 2013 and switch to blockchain, mainly Ethereum and smart contract things in 2017. So in that 2 moments, I have the chance to find a lot of interesting findings. If you, I previously worked for Keyhoe 360, and we submit like hundreds of bugs to Google. And also, I co-founded Paxio, the security firm, and we did find lots of smart contract bugs. So NTFS3 is actually something that hit our mind and just show up in our radar, because NTFS3 is actually the first fully functional NTFS third-party implementation in the Linux kernel. So in the past 3 decades, we actually have multiple different implementation of NTFS in Linux kernel, but none of them is fully function. And so, I mean, it's complicated enough to have some bugs. We know that we will find something. And also, the other thing is that fuzzing operating system, or we say fuzzing Linux kernel, is not an easy task. And also, file system has some more factors attack surfaces, like they have the file system image and they have the format. If you just randomly generate system codes, file operations with syzkaller or some other OS fuzzer, actually you cannot efficiently fuzz the file system. So yeah, that's the motivation. And a little bit background about NTFS. I think I talked most of them already. So NTFS was, the first release of NTFS was released with Windows NT 3.1 in 1993, 30 years ago. And the last 3 decades, we have the read-only NTFS implementation in Linux, also the NTFS3G, which is using the user mode fuse file system to help Linux users to mount a NTFS image or drive. And yeah, just the end of 2021, 2 years ago, less than 2 years ago, we finally get the NTFS3. Actually, we found that NTFS3 was upstream, and we think it's really a good target for security research. So yeah, that's why. So I'll go through a little bit background about file system and the attack surface, because when you try to fuzz something, you need to find the attack surface and how you can generate inputs to make the system crash and burn, and then you can, if you luckily can reproduce that crash, and you may find some 0 days. So when a user accesses a file in the file system, the first thing is that he or she need to mount the file system drive, for example, NTFS drive or image. So that's the very first thing he need to do is the mount system code. And then he can, at the mount point, he can open the file, rewrite the file. So there are actually 2 attack surfaces. The first one is mount. When you mount a file system, a bad actor can actually create mailphone images. Like the operating system, the file system mount handler will parse those data. And if that data has some like offset or memory pointer or some calculation, you may have the chance to use a mailphone image to crash the system. And also, all the files operation has lots of different combination of parameters. So that's the 2 attack vectors that a attacker or security researcher can attack the system, the file system. So then as we know that these 2 attack vectors, then we need to choose a weapon to both generate the mailphone image or whatever image to crash the system, and also you need to generate all the system code to randomly generate all the parameters to crash it. So, but actually, when we say that when we try to fuzz something with the format, AFL would be maybe the best choice, or all the fuzzer derived from AFL. And when we're talking about system code, syzkaller must be the one. But actually, we don't have a perfect one to combine both of them. And the other factor is that we need an efficient software or mechanism to efficiently run the target. Because when you're fuzzing the OS, there's a so-called agent issue. Like when you boot up the operating system and you mount different, like 10 different fuzzing images and perform lots of fuzzing operations. And finally, the last, maybe the right system code, in the end, crash the system. But you don't know exactly what happens in that 10 different images and all the file system operation in the middle. So when we fuzz the operating system or file system inside the operating system, we always need a fresh OS instance. So you can use real machine to do that, but you need to buy a lot of machine, and you can also use VM to spawn lots of different OS instances, but that will cause you consume a lot of memory. So we need something in between. So actually, we found one fuzzer framework. It is perfectly match all the requirements, which is Janus, published by Georgia Tech SS Lab in IEEE SMP 2019. So Janus could be a candidate for fuzzing or target the NTFS3, but we soon realized that it actually requires us to rewrite a new parser specific for the NTFS. And also, I said the libOS-based kernel executor. In Janus, they use the so-called LKL Linux kernel library to do that, but we found that the LKL was not maintained anymore. So we need to port that LKL to the latest Linux kernel. And also the other thing is that we also need Kson and something similar to help us to catch all the memory issue as early as possible. So yeah, we based on the idea and some framework about Janus, we built our own one. And yeah, I think then I'll hand over to Edward, and he will explain all the how we deal with those challenges and all the technical details.
Okay. My colleague just explained all the motivations about why we choose NTFS, gave a brief introduction to Linux file system, the possible attack surfaces, and available choices for file system fuzzing. I'll continue to walk you through the details of our approach, the implementation, how we resolve the challenges, and some case reviews in the end. But first, I want to check our fuzzer status because, people always say talk is cheap. We need to prove that our fuzzer is really working. So,
no, it's good.
okay, finger crossed.
Yeah, I think we found something.
So let me switch to. Yeah.
Okay.
Okay.
Good.
You see that? We've got 2 crashes already. So I think I just proved it. It's working. It's effective. It's efficient. It got 2 crashes in 11 minutes. So that's pretty amazing for a fuzzer. But actually, here's a tricky part. Getting crashes doesn't mean it's 100% reproducible. Sometimes they are really hard to try it, to find root cause, and sometimes they are just for so long. But we'll try to these issues after Q&A if we have time. Okay, so let's get back to our topic. Okay. Okay, so what's all the challenges to file system fuzzing? The first challenge is that file systems are large, but only metadata matters. And if we want to extract this metadata from the image, we need to write the image parser because each file system has its own design. So there's no general solution. Wait. Okay, so sorry, I had to. No. Just let me. sorry, let me, okay. Yes, we need to develop a specific parser for the file system and checksums. They are bound to fuzzers. If we can, if the file system has its own mechanism or checksum for its metadata, we need to recalculate and fill in these values after the mutation. Otherwise, the file system will reject to mount the image. Okay. Yeah, so here's the brief introduction to the image, NTFS image format. The first sector is called partition boot sector, which holds boot information and some important fields. For example, bytes per sector indicates number of bytes per disk sector, and sector per cluster is the number of sectors in a cluster. And we have MFT, which is a master file table. NTFS stores all the information in the MFT table. The first entry is the MFT itself, and the second entry is MFT mirror, which holds the duplicate of the first four entries of MFT. Okay. Oh, sorry. And the last is user data. We don't care about this data while fuzzing the volume. So NTFS3 has some sanity checks other than the checksums. The OEM ID, it must equals to NTFS and 4 spaces. It will return error and solve the mounting if not. Wait. And also the sector size. It should be larger than 512 bytes, and there must be a power of 2. And the cluster size, it must be a power of 2. If any of these sanity check fails, the file system, the NTFS3 driver will reject and fail the mounting process. Sorry, just, okay. Oh. Okay, so as we mentioned before, the allocation unit in NTFS is cluster, which is a collection of sectors. NTFS applies a mechanism called FixUp to protect the integrity of the each sector of the metadata, so that you will be able to detect corrupted sectors in a cluster. But not all metadata applies this protection, only the important ones. Like the file records in MFT, or directory records, or directories, record in directories. Okay, so how is FixUp working? Assuming now we are writing to a file record in the MFT, the header of the file record contains the field, update sequence number, and an array buffer for each sector of the record. Before writing, the reuse n is incremented by 1, 1, 2, 3, 4 to 1, 2, 3, 5. Then it will copy the last 2 bytes of each sector into the update sequence array. Okay, so to the sequence array, and you write the new SN to the end of each sector. Okay, then S it will return back to the disk. And here's the corresponding code for the FixUp logic before writing. FixUp is the term used in the implementation. It is the synonym for USN. The FixUp offset and the size of the FixUp array are retrieved from record header, and some sanity checks applied here. And in the middle, you can see that the FixUp is incremented by 1, and you wrap that back down to 1 if it reaches the FFF. And we have a loop here that will put the FixUp to the sectors of the array. On the contrary, the reading flow is basically the opposite of writing. After reading the contents from disk, NTFS will first check the USN against each last 2 bytes of the sectors in the record. The values should all be the same as the writing flow we described before, or it may indicate the bad sectors or disk corruptions. And if the check is passed, the NTFS will copy the corresponding fixup back to the last 2 bytes of each sector. Here, okay. Here's the code for reading. Same as writing. The fixup of set and size are retrieved from record header, applying the send sanity check. And at the end, the loop is responsible for checking whether USN and the last 2 bytes of current sectors match. If not, it won't break a loop, but it will return an error code in the end. Okay. So we've already expressed the challenges for image fuzzing. And so how does Papalo solve these challenges? First, it only extracts metadata from the image and feed it to the mutator, which could save lots of time because only metadata is mutated and no user data involved. And second, the image parser will fill in legit values after the mutation. For example, it will replace the OEM ID, make sure it equals NTFS and 4 spaces, and the sector size. It will wrap down to the nearest power of 2. So say if the mutation, after mutation, we have 1050, it will replace with 1024. And combined with the adjusted metadata with user data, we have an image that can be successfully mounted by our executor. Okay, another attack vector is the file operation, which brings another challenge to file system fuzzing. An effective fuzzer needs to know what system codes to generate. They must be file operation related. How to mutate the parameters of these generated system codes? If the fuzzer is mutating the parameter for a read system code, the first parameter must be a valid file descriptor, as the second parameter is the buffer, and third is the buffer size. Simply randomly generating parameters to the system code is meaningless because you'll just get lost variable code returned or get your executor terminated by some exceptions. And how to make the fuzzer context aware? How to link these generated system codes? The fuzzer should maintain the context across each system code. Here's an example. So if the fuzzer generate a new open system code, if the path exists or the mode or flag is permitted, and it will get a valid file descriptor returned. And the file descriptor should be kept in the program's context. So if the fuzzer wants to mutate the system code, which takes file descriptor for parameter, for example, read, write, or close, or any other system code that takes file descriptor, then it could get the valid file descriptor from the context. Okay, the following graph shows the flow of system code fuzzing in Papalo. The C program is derived by a set of tools, which are also part of the Papalo fuzzer. You can check README for detailed instructions. The C program itself is a serialized format, contains variables, system codes, and file objects. The first phase is mutate. Papalo will randomly choose system codes from the C program's context and mutate its parameter accordingly. And if there's no interesting outcome, it will switch to phase 2, generate. It will generate new system codes and update the context accordingly. So if there's new file open for new file descriptor, it will keep it in the context. Okay, now we've already solved two challenges, limit fuzzing and the system code fuzzing. The last consideration is how to run the test case, how to choose your executor. Here are the comparisons between a real device and virtual machine. The real machine is faster than virtual machine, that's for sure. But the virtual machine has better scalability. You can scale just by run more VM instances if the memory is allowed. But on the other hand, if you want to scale a real device, you must buy more devices. Also, the virtual machine is easier to manage. You can manage them by some scripts or by some scripts. But if you want to manage the real machine, you may need some devices. For example, debug board, or some real hardware devices. Also, the real machine is risky because you may break your device. Okay, so instead of using real machine or virtual machine, Poplar utilizes libOS executor as Janus. The executor links with Linux kernel as a library, the LKL, which is a project to compile Linux kernel code into an object file that can be directly linked by applications. So basically, the executor is a USML application with kernel functionalities. So our executor is fast as a USML program, and it's easy to manage, and it's easy to scale, and more importantly, it's easy to reproduce because not like the real machine or virtual machine, they had unstable or aging kernel. But it also has some deficiencies. So for example, LKL itself is implemented as an architecture, and it has some limitations in current implementation. It has no MMU, so no virtual memory support, and it is an uniprocessor architecture. Also, it is not in the main line, and it is also sometimes inactive sometimes. So if you need the latest kernel, you may need to do the kernel upgrading yourself. Okay. So this diagram here shows the whole workflow of Poplar. First, combining the seed image and the seed program, we'll get the initial corpus. The image parser will extract metadata from the seed image and then pass it to the image mutator, and we'll fix the key field values after mutation, and finally replace the last 2 bytes of some sectors in a cluster with correct fix-up values. And then we'll pass it to the executor, so we can successfully mount the image and start our fuzzing to mount flow. And if there's no new coverage or any new crash case, it will move to second phase, which is file system code fuzzing. The first step is to mutate existing file system codes parameters, and if there's no new corpus, no new coverage or crash case, you'll move to the second phase of the file system file operation fuzzing to generate new file system codes. Okay, so far we've already covered the design and workflow of our approach. But actually, when we knew that NTFS3 was going to merge into mainline, we chose the most promising solution back then, this famous syzkaller. We ran it for months with a customized syslen description that contains file operation related system only, but no interesting outcome. And we did some surveys, and we find Janus, but as we already explained, we are still missing the image parser, the NTFS image parser, and the upgrading. We need to upgrade the libOS, the LKL, to the latest kernel, and some functionality. For example, the case and patch integration. Okay. Yeah, okay, so in the end, we identify 12 issues. Actually, it's currently 14 issues. The maintainer just replied me a couple days ago. And as listed in the table, we'll have these issues. We categorize these issues into 2 types. The green one is type 1, which can be triggered by mounting the image. And purple color is type 2, which can be triggered by mounting the image and with some preparations. We'll review these issues one for each kind. Okay, so this is a type 1 issue, which can be triggered by mounting the mutated image. We have already seen PBS and important metadata located at the first sector of the NTFS volume. And there's a critical field called the MFT entry. MFT entry size in PBS, which specifies the size of an MFT entry. If the value is positive, which denotes the number of cluster of an MFT entry. So if it's 1, it means 1 cluster. We can get the real size by multiplying the bytes per sector and sectors per cluster. A negative value denotes the number of bytes of an MFT entry, in which case, if we have a F6, which is minus 10 for a signed byte value, then we'll have the real value is 2 to the power of 10, so which is 1024. Okay, so here's the stack backtrace, and on the left side is the backtrace of this issue. We can tell that it is MPD from the first line. The backtrace shows the kernel crash while mounting the image. Okay, and the right diagram tells the details of the NTFS image mounting. We can map it back to the stack backtrace. The mount flow starts from the mail system code and all the way to the file system implementation. For example, NTFS FixUp. Okay, so what is the root cause of the MPD issue? NTFS FixUp will call NTFS init from boot, which is a function for PBS parsing. And it will calculate the MFT record size by the formula we expressed. Before, then it will get the record bits by the block size bits function. But however, it has an assumption. It assumes that the size is always larger than 256. So you can see the initial value, return value is 8, and we have a do while loop. So it will increase it by 1. So the smallest return value is 9. Okay, so, but if we have a record size, which is FA, then it's minus A for our signed byte value. Then we'll have the real value is 2 to the power of A, which is 256. But the record base is 9. So we have a mismatch here, which will lead to an MPD issue. And here's the patch. It's pretty straightforward. We just add a check that the record size is equal or larger than our sector size to support the assumption. Okay, here's the example of type 2 issue with CBL sign. We have already introduced MFT earlier. So a table that stores all information of files or directories of NTFS volume. The upper right diagram represents a simplified MFT entry format. It starts with a record header and an attribute array, and with the first field is the attribute type, and the second is the size, and the third field is the non-resident, which indicates whether this attribute is resident or non-resident. A resident attribute means its data can fit into the MFT entry. Okay, so let's take a look at the backtrace of the kernel crash. It is a slab out of bound write. So it's possible to exploit this vulnerability. We can tell that the root cause is somewhere when user code set X attribute system code, all the way to NI create attribute list, then trigger the KSN while copying memory content. So the image must has been already successfully mounted. Okay, the right side is the KSN report, which tells us that the address belongs to a 1K size buffer. Now, we know the root cause probably lies in the NI create attribute list, so our investigation starts right there. First, it allocates 1K size buffer for attribute list entry. And remember, the KSN report told us the outbound write address belongs to a 1K size. Then there's a for loop to enumerate the attribute by calling mi non-attribute. And it has some checks, sanity checks for the size of the attributes. For the non-resident attribute, check the size and the offset, make sure it won't cause any outbound write, and return it immediately if the check is passed. However, it missed the sanity check for attribute name length and offset as the non-resident attribute at the bottom. You can see that check. It missed for the resident attribute. So if a malicious attacker intentionally crafted some attribute with malicious attribute name and length, it could lead to outbound write, which can be used or exploited by experienced attacker. And yes, patch, we just add the missing part for attribute name length and offset for the resident attribute. Okay, we've already elaborated the architecture and fuzzing flow of Apollo. So we've proved that it's an effective and efficient fuzzer, currently targeting NTFS, but easy to extend to other file systems. We also reviewed some of the issues identified by Apollo, one for each kind. And here's our conclusion. Complicated systems is always a good target for security researchers because more complicated, the higher possibility there's a vulnerability in the system. That's for sure. Second, file system maintainers should pay more attention to the metadata integrity. We've seen several cases that caused by blindly trusting the metadata retrieved from the image. And last, users should be cautious on mounting a disk image. If you have concern, use Sandbox or VM if you don't trust the source. Okay, I think that's all for our fuzzer.
We don't have time for that.
Oh,
yeah, we run out of time, so I'm sorry about that. So if you have more questions, we can talk offline. Thank you.
Thank you.